If I can take my control points and manipulate them by 20 centimeters like I'm doing here, and yet I arrive with an error estimate as low as this, surely there's got to be a problem. Let's learn how to use our markers and GCPs in Metashape the right way. To begin, go about performing your alignment process as you usually would. And if you're unsure on how to do that, I'm going to leave a link at the top of the screen now. In addition to the alignment process, you also want to be sure to tidy up your tie points as best as possible, so that the data set and camera alignment that results is as accurate as it can be before we go about marking the GCPs. Once the alignment process is completed, it's a very good idea to take a look at the values of that alignment or the error. So focus in the reference pane on the error column and move to the bottom and look at the average. In this case, it's 18 centimeters. This is an RTK dataset, so we do expect it to be quite good. If you aren't using RTK or PPK, it will possibly be much higher than this. In addition, let's look at how the camera calibration parameters have been derived. The initial value of 4,417 micron for the focal length is a mathematical operation. You take your focal length in millimeters, in this case 10.6, and you divide it by the pixel size of your sensor, and here it is 2.3 micron. The result of that mathematical operation will be the focal length in micron. Now have a look at the adjusted value or the calculated value based on your image positions. Here we have 4,403, so it's only a few micron different from the initial or calculated value. If this is 5 or 10% different, I would definitely start to worry. Go back to your alignment process and try it again. Something would have gone wrong. And pay attention to that value throughout your processing steps. Now we want to load in our GCPs. Select your file, make sure that you have the correct coordinate system, set the values as you need them, and load them in. The software will note that none of those values match your images, so say yes to all, and it will load them onto the screen like this. Here you'll see the little flags for the GCPs don't match the data, and that's because we are using two different coordinate systems. So you'll need to convert your image coordinate system to match. In this case, we can't do it right away because the camera reference is incorrect, so ensure that you set your camera reference and your working coordinate system accurately, and then we have alignment. I like to use the same system for my images and my markers, so convert the reference so that the values all align with each other. Now we can go about aligning the markers one by one. Before we do that, it's a good idea to pay attention to the reference settings. You'll see in this case, camera accuracy is 10 meters, but our marker accuracy is 5 millimeters. These values are vitally important and are going to have a big impact on how accurate the marker alignment is at the end of the day. So we start by selecting our marker, right-click, filter, and we want to drag the marker to the center of the control point that was placed on the ground. The first two will likely be a little bit off from the mark, but from the third point onwards, they should start to be more or less in the center of your marker. Again, if you aren't using RTK or PPK, these will be far further off to begin with, but as you add the markers, they will tend to move to the middle of those positions. Then I want to look for a point on the other side of my data set. I don't want to just do the next point. I want to go to the opposite end of the data set, select a marker, and align it again like we're doing here on screen now. Now, once you've done all of those, we're going to firstly adjust the positioning of our data set as a whole. And this is important because we don't want to just go ahead and recalibrate the camera, because if we do that, it's going to manipulate the camera values to make sure we have alignment. I'm just aligning a third marker first, and then what I'm going to do is move the data into a horizontal or a transverse viewing position so that we can see what happens. Now I want you to pay close attention to the tie points here as we hit the convert button and watch how they move ever so slightly. You see it? So what's happening there is we're applying an average shift to the position of the images. We then go ahead and we can add the rest of the markers. The reason we want to apply that average shift is so that we don't just go ahead and manipulate the camera calibration to make the images fit the control points. It's a very important step, especially if your marker positions are further off than what they are in the case of this data set that I'm using. So once all is said and done, notice how the error of our image positions has changed quite significantly, but the error of our markers is quite low at 1.8 centimeters. I'm only now going to optimize the camera calibration and the camera positions and see what those values come down to. So we see after that process, we've come down to an error of 1 meter on images, but 8 millimeters for the marker accuracy. Now, the fact of the matter is that is an unbelievably good value. It's too good to be true. What I want to do now is set my camera accuracy to something more realistic, let's say 3 meters, and my marker, my GCP, to 2 centimeters. Unless your surveyor has done the world's best network calculation, the markers will not be 5 millimeters accurate. I'm now going to recalibrate the camera and have a look at what result we get. We'll see 3 centimeters already, and then 3 and a bit, nearly 4 centimeters. And that is a far more realistic value that we have between the alignment of our images and our control points. If we have these values set too high, like it is here, 10 meters, and the marker accuracy too low, we are only achieving a false accuracy. So we need to be very careful of that, and I'm going to demonstrate the danger of it soon. So what we need to be aware of is that the software will always do its very best to come to a zero-sum solution. The software is just trying to reduce the error. It's not really paying attention to best survey practice or photogrammetric principles. It's using mathematics to reduce the error as best it can. So if I take a control point and I'm going to adjust it, manipulate it by 20 centimeters now, and I want to show you the danger of leaving those values too low. So here I've shifted it by 20 centimeters in easting and northing, and we see initially the error is 22 centimeters. So that makes sense. I'm going to adjust my camera and see what the result is. And once that processing is done, we see it's still relatively high at 16 centimeters, so it has reduced it. But now I'm going to go back and edit this marker accuracy to what it was, to that 5 mils. And look what happens to this value. 1.8 centimeters total error. And we know that that's absurd. That possibly can't be, because we've just shifted the data by 20 centimeters. So that just goes to show that if you leave that marker accuracy too low at 5 mils, you will run into problems. Here's another demonstration. I'm going to adjust every altitude value for the markers by 5 meters. So we know we're introducing a 5 meter error. Again, adjust and optimize the camera parameters, and look what happens. When we do that, again, we have another false error that is incredibly low. Again, too good to be true. But here's an indicator. Look at the error estimate of your camera position. Suddenly that shot up to very nearly 6 meters. Remember earlier we had it at around 1 meter. So that is another indicator that there is a problem. Don't rely purely on what your markers tell you, because even if we look at the focal length, that value still looks quite good. So the camera positioning error is where we're going to see the problem. Okay, so what do we do to get around this problem? What is the right way to go about processing? Start off by setting your camera accuracy to something that is logical or makes sense. In this case, RTK, 3 meters is acceptable. If you have PPK, maybe you'll drop that down to something much lower, 30 centimeters perhaps. Even better than that in some cases. You then want to not try to just reduce the error value of those markers down to 0. You want to be cognizant of the fact that there could be mistakes in your GCPs. The land surveyor could have made a mistake in his calculations or in his observations. Unless you receive a survey report with a perfect network calculation with all the values showing that every point is most definitely 5 millimeters or less, don't set the value to something that is unrealistic. Generate the reports and have a look, because these are the kind of values that you're sending to your clients. You don't want to be lying to your client or pretending that your data is more accurate than what it is in reality. In this case, let's just go back and look at those camera locations. You'll see that there's a very average or systematic shift towards the northeast. So that's good. And have a look at the control points now. The total area there at the bottom of 1.7 centimeters, far more realistic than 7 millimeters. So this would be a better result to deliver if we aren't using checkpoints. But of course, the best way to process is control points and checkpoints. Let's look at how to do that. Now, what you want to do is select from your set of GCPs those that you will use as control points, but some that you might use as checkpoints. So effectively, we want to discard or temporarily remove a few of these points. So in this case, I'm just having a look at the positioning of all of the points and seeing which could be excluded, but we still want to ensure that we have total coverage across the data set. So I'm going to take off marker 3, 4, and 8. And by doing that, it looks like we'll still have a good coverage across the data set, but we now have 3 markers that we can compare. And those 3 markers will actually denote the accuracy of the data at the end of the day, not the control points that we're using. So 3, 4, and 7, those will give us our accuracy. The rest of the points will only tell us how well we have managed to shift and fit the image positions and resulting data to those points. So again, I'm going to select the first marker, which is at the bottom right-hand corner, and then something from the upper left-hand corner. And I'm going to disable 3, 4, and 8, our checkpoints, before I do this update transform procedure, because I want to exclude them from the operation entirely. They must be independent. Then go ahead and check the rest of your markers. The same way that you would normally do this, update as you go along. And once you've got right to the end and you've done all of them, we then want to go back and visit the checkpoints that we've placed. So we still aren't optimizing the cameras. So change the selection criteria, go to your checkpoints, and now place the checkpoints as well. But in this case, you will not update the transformation and you will not optimize the cameras based on these positions, because again, we want them to be completely independent. Now, once you've marked all of them, change the selection criteria again, and now we start to see the realistic result of our processing. So update, optimize your cameras. And once we've done all of this, the checkpoint value that you see at the bottom is going to give you an accurate representation of your data set. That is the accuracy that you can actually quote your client when client asks how accurate it is. Note here, if I shift it down to a 1 centimeter accuracy on the checkpoints, how not the checkpoints, on the control points. The control point value changes somewhat, but the checkpoint value stays the same. And this is vitally important. That is your accuracy, not the marker accuracy. Output your report as well. Now your report has far more meaning, because we're not just showing how closely we have aligned the images to a set of points, but we're actually able now to speak to the accuracy of the data in between all of those control points. So 6 centimeters that we see here on our checkpoints, far more realistic value for your data set as a whole. So please, a word of caution, look at those values in those reference settings. Make sure that they are something that is representative of reality, not a false 5 millimeters. It is very, very rare to have any control points in this day and age that are actually accurate to 5 millimeters, unless your surveyor has done a full network calculation.